their height, width, depth and position in relative to one another. Okay? So to do that we must measure things. And the two things that we do of course in science is we use rulers, microscopes. This is a graticule, okay? We put them underneath a microscope that allows us to calibrate the pixels so we know how much each pixel actually weighs, what the dimensions of it is. What you're looking at there is actually a centimetre, and then we divide it up, and we divide it up, and we divide it up. I work in a world of small things, very beautiful things, but very small things. So of course we work across the scales as microscopists and people who are working in imaging. Centimetre, milli, micro, nano, pico, femto, atto. Across that whole scale, we're involved in physics that are on those scales. I quite like saying to people that I work with some techniques that actually work on the quintillionth scale of seconds, trying to make two photons hit at the same time. That's pretty cool. The other one, of course, is time. And we are quite accountant with time, and when we're looking at cells and molecules and proteins moving around, we don't work on the second time scale. We've been working with light, we're looking at nanometer type precision that's happening over a very, very fast time. So, I want to give you the right perspective and get you to start thinking about how different things start looking. And so begins the trivial pursuit with chocolate for dessert. So, I'm going to show you some microscope images done on a humble light microscope, and of course beautified, because that's what we like to do. And you're going to have to guess what they are. And I'll give you a subtle hint. Okay? First one who yells out the answer, this could be problematic, gets the chocolate bar. Make sense? Everyone's clear?
Game on.
Game on.
Is it a tongue?
No. What you're looking at there, those little nodules, they're about 1/3 the diameter of a hair, which is somewhere between 70 and 200 microns. So they're about 20 microns across. They are used, or an offshoot of them, is one of the main ingredients in Turkish delight.
Gelatin.
Pardon?
Gelatin?
No.
Disgusting.
No.
Rosebud?
What did you say?
Is it a rosebud?
Yes, it's rose. And actually, those are papillae. It's actually what gives the rose the satiny gloss that we actually see. Okay?
Bed bug.
Oh, lice.
Pardon?
Bed bug.
No, it's not bed bug.
Lice. I'm diabetic.
Never had it.
Lice.
But there were
That is
others
beyond.
as well who said it.
You said it?
Never had it. There were others as well. So
Right. So, what people know about lice, and of course anyone who has children knows that it's not a very pleasant thing to have, is actually lice that you're looking at like this have actually started to become resistant to the treatment in hair. And so there is now people going back to using tea tree oil and these sorts of things, super lice. It's pretty scary.
they're very resistant.
Oh, I know.
Velcro.
Yeah. Yeah, good on
Velcro.
Velcro. Okay. Made the astronauts. Okay. Went to the moon. One of the first materials to go to the moon. And this one's gross. Those fibres that you're looking at are about the width of hair again, and they come in mint, cinnamon, and bacon flavour. What is that image?
Should we go?
Nope.
Is it mint?
Bacon sugar?
As funny as I think it could it be toothpaste?
It's not, but you're getting close.
It's other toothbrush.
Toothbrush fibre.
You said it. No.
Floss.
That is, you get these. Not only is it floss, it's used floss.
Did anyone actually say that? I didn't feel I deserved these, but I kind of knew I deserved it.
Just take the try.
Thank you.
This food that we eat has the second highest level of, I'm trying to think what it's called now, lycopene. Okay?
I want tomato sauce.
Correct. Known to reduce cancer in men by 30%. Okay? The highest one comes from watermelon. Get into that watermelon, right? So of course, all of these images come from a microscope. Now, microscopes are not all created equal. Okay? Some of the more nerdy scientists as kids probably had a little microscope and we went around putting things underneath it all the time. And indeed, you can buy a single eyepiece little microscope at Australian Geographic for about $80. I know what my daughter's getting for her birthday. But Australians aren't, right? However, the microscopes that we use are not microscopes like this. Okay, and there are some other microscopists in the audience, and so they know well and truly. Microscopes that you see, for example, on the right-hand side are confocal microscopes. They have different sorts of detectors. We use lasers. We can capture lots and lots of photons. They use a pinhole and lots of mirrors. Same thing about perspective. However, they don't cost $80. Not surprisingly. I have $13 million worth of microscopes in my lab. Okay? One like that you see there is in the order of between 350 and 500K. Okay? These are scientific tools that can do some really remarkable stuff. So people often ask me, how on earth did I end up getting into microscopy? It's a bit of an odd thing to do. So circa 2001, I was doing honours. Actually, that was 2002 March. For those of you who can check out some of the time clues here. I was very into the Lord of the Rings at the time, so this was March 2002. It's giving me inspiration. I was a chemist, okay? That's what I had my PhD in. And what I did was I made a series of anti-cancer drugs. It was something that was really important to me. My mother had been diagnosed with breast cancer. She was one of only two that survived, okay? And actually that very same year, one of my dear mates, who was 28 years old, was also diagnosed with breast cancer. She didn't make the cut, okay? So for me, I had a connection with what I was doing in that space and the reason why I was there. Sometimes we choose occupations that do those sorts of things. You will note, though you can't actually see it on this image because it's been cut up, actually up what it says here, it says do not drink. So it was a bit of a motivation. I don't think it was me. So what was I doing? I was making a whole heap of drugs. I was making, using a combination of two anti-cancer drugs that people use in the market. One's called doxorubicin, my mum took it. The other one's cisplatin, my friend that died. What we were doing is we were trying to combine these and mash them up to try and make them better at doing what they were supposed to do. And the main reason how they work is by they interact with DNA. Okay? And to get in through the cell, they have to interact with a specific DNA target. So we were trying to mess these around and test that they were actually doing what they were supposed to do. So to do that, we did some typical chemistry type experiments. You know, we did a lot of pipetting. We did some modelling with DNA. We did some 2D NMR. I even broached out wild in chemistry. I started doing cell work and testing the cytotoxicity. Woohoo! But none of these actually specifically told me whether or not my drug was getting into the nucleus and getting to DNA. They were all in vitro experiments. So again, I went off to the microscopy facility, Okay, better test this out. I was very lucky these drugs were fluorescent, so the lab knew how to look at them. And I was sitting down and I put my drugs underneath the microscope. And everyone else in the lab, none of their drugs were making it to the nucleus. Right? So we were all a little bit. The first thing that I saw was this. Now, for those of you who are not familiar with cell biology, this is the nucleus, which ended in me doing something like this. It's in the nucleus! It's in the nucleus! It's in the nucleus! And my poor trainer at the time, I gave him the high note. I said, it's in the nucleus! And then I was a bit of a mad scientist running through the school of chemistry. My supervisor was teaching third year chemistry and went, it's in the nucleus! Everyone thought I was a bit mad. It's a bit of a mad scientist. Therein I got perspective about what I was supposed to do. And for me it was by far more important to start using lots of microscopy and training lots of people to use microscopes, because I felt I was going to be much better at trying to help more people in that way. That's why I am here. Okay? So, this is what some of these microscopes look like. They don't really look like microscopes very much anymore. This one does. You like her. This one's a single molecule microscope. You can actually see single molecules moving around them. Watching them bind to DNA, watch RNA polymerase bind to DNA and measure the kinetics. Life cell imaging. Okay? You keep the temperature and the humidity and everything just right, and we keep cancer cells or cells alive for a really long time when we test drugs and do those sorts of things. One up the top, that's my new baby. That's called a light sheet. Okay? I can make 90 terabytes in a day. Okay? It's pretty cool. But it means it's pretty expensive. It's not quite JPEG. So what sort of images do these microscopes take? Okay, that's histology. It's a standard H&E. If you get a biopsy, it gets sent away, and people screen these for different drugs, and then people have a look and they test whether their drugs are useful against this or this specific drug. Now, that's a cancer cell. Okay. What you're seeing it do is actually crawl along collagen fibres, things that actually make and mesh up all your cells together. What we do is we can see the cancer cells actually grabbing hold of the collagen fibres to pull themselves along. Pretty freaky, right? What does it remind you of? It's what it is. It's cardiomyocytes. Okay? So we take cardiomyocytes and we monitor the beating frequency, and then we can treat them with different drugs like doxorubicin. One of the biggest side effects is cardiotoxicity. How does it affect the beating? Okay? One of the most important things that we use is fluorescent. Without going into enormous details, what it means is that it's a specific sort of chemical. It's dark. We hit it with a bit of light, and then it goes a specific colour. Okay? Don't need to know any more than that. Other than, of course, it happens really quickly, a lot faster than what I just did. Okay? Most of you, is anyone drinking a gin and tonic? Anyone who's gone to a club, ever looked at your gin and tonic, you would see that it's fluorescent. Someone puts salt in it, it'll quench it for you, by the way. You don't really want that.
When was that? When salt in what?
There's a chemical in tonic water called quinine that's fluorescent. You can actually turn off the fluorescence by using certain image on the right. No, it's not my daughter drawing me pretty pictures again. She's much better than that, actually. What that is a new technology that someone won a Nobel Prize for. It's called green fluorescent protein. Okay, and they can lock in any gene, change a protein or an enzyme to fluoresce by putting in a different colour. So what you're looking at there is actually agar paint. Okay, there's a whole series of different coloured bacteria that are on there, and then they've gone and drawn on these with light. Fluorescence, very pretty, right? Starting to see that it looks a bit more like art now, but in reality there is a lot of science behind what you're looking at. You look up in the top right and you're looking at cancer cells, and we can see all the different organelles and see what happens over time. Image on the right is an aorta, and actually what you're looking at is a plaque formation. Okay, so we look at different effects like what happens with impaired cholesterol and these sorts of things. Down here, stem cells. Okay, lots of people get a bit weirded out by stem cells. People can now take adult stem cells, reverse them back to be like that can go into any other cell that they want to. These ones have gone into neurons, okay, generated actual real connections and communicating with one another. On the right, understanding how development works, how do cells actually become cells. A lot of information for something that's very pretty, right? Perhaps one of the most important things that most of these microscopes do is that it gives us three-dimensionality. Okay? So what we do is we take those planes and we go through with either the injective or a very fast piezo stage, and we can step through. Image on the top right is a tumour spheroid. We make spheroids with cancer cells, so we mimic a mini tumour. Okay? That's been treated with fluorescence, and you can work out whether your drug's actually making it to the centre of the tumour. What you're looking at here is a light sheet image. Okay, that's actually a spine, and it's actually had a spinal cord injury. And so then we can measure, put retrograde traces in and see them. Pretty cool. Image on your far right, down the bottom. Whose parents have stents? Anyone? My dad's got 6. My mom's got 3. It's the nature of cardiovascular disease. This is a specialised coded stent. So we start to work out whether cells are doing the right things with stents that are not going to stop clotting form later on. The fourth dimension, also equally important that we get. And when we start to talk about fast, are you going to work for me? Who wants to? Maybe the arrow. Yeah. But I want this one. Okay. Those are neurons. What we're actually looking at there is the calcium process as they actually talk to one another. This means that you've got an image in the order of about 200 frames per second. When you're watching a DVD, 30 frames per second. Okay? We have cameras on some of our microscopes that can take 22,000 frames per second. That's pretty cool. It's not a lot of light around there, so it's a bit of a balance. But yes, can we go that fast? Yes, we can. And the sort of processes we can see at that time are very different. Again, about perspective. I've shown you a lot of very pretty images, but I always want to show you that all of this state-of-the-art equipment also requires researchers and technicians, and there's some people in here right now that are actually do this as a living, optimising this so we actually can see what we want to see and get the perspective from research. Okay? It doesn't always work. So here is an example of cells that we want to image over time. You can see that if it doesn't work, goes out of focus, dries up, cells all pop. Failed experiment. Okay? All of the technology in the world is not going to help you if you don't set it up correctly or the microscope is not working. So I want to come back to perspective because I want to finish with this because there are a couple of last things I want to talk to you about. The first thing is I want to go back and talk about what the right impression is that you get from microscopy data. Just because you see, do you believe? Is that what you should be doing? And of course, perspective, in its final form, true understanding of the relative importance of things, the sense of proportion. Now, to me as a scientist, that means quantification. And yes, microscopy is for quantification, as well as it being for beauty. However, we can't always trust it, right? So, you have a look at the image there. What you're looking at is a cell that's got one item labelled with red and one item that's labelled with green. When you lay these over on an image, they end up being yellow. This is the way they combine in the image. Now, if we see yellow in a pixel, what that tells us is those two things are together. Okay? They're interacting. However, there is a thing in microscopy called resolution. Okay? And for us, resolution is by far more important than magnification. Okay? Because if we get it wrong, then we start to make decisions that might not necessarily be correct. For example, are these correct? Well, fortunately for us, there was a Nobel Prize awarded for what we refer to as super resolution in 2014. So what you can see there is what we refer to as a steady image. And the science behind these techniques is about manipulating that fluorescence turning on and turning off. And we just manipulate it to be able to do that. To give you an idea, what you're looking at here, and it's not great on this screen, is that we've got about 20 nanometre, 30 nanometre type resolution, which is pretty cool. Gone are the days where the best you're going to see on a microscope is 200 nanometres. So of course, quantification can be done on a microscope, and a lot of it does have to do with how you save your data. We don't save these sort of things. Okay? We want to be able to know that every pixel that we're looking at, that intensity value is actually going to give us the right numbers. We don't manipulate them. Okay? But there's lots of things that we can work out from microscopy. What size is it? It's really easy. How frequently does it occur? Is there a difference between 71 and 72? All of this means that you've got to use a microscope in a very specific way to gain that perspective. And of course, then you get down to things like, does X interact with Y? A lot more difficult than lots of other people, lots of microscopists know to be true. Okay. So, in other words, you can answer pretty much any scientific question and quantify it within reason. So is microscopy art or science? I'm going to leave you to come up with your own decision. Okay? But know that lots of people have capitalised on this. Okay? Some of the probes now, you can send your image in and get it turned into a colouring in book image. I can just see the pleasure on my daughter's face in colouring in a cell and all of the organelles. Not so sure. Maybe that's once to be adults. The image on the right is of a vodka and tonic. Okay? It took 200 times to take that image. That is art for one image.
Just call it the art of science.
Call it the art of science. Yeah, maybe. Everyone thinks of it a little bit different. There is definitely art, people who manipulate or use science for art.
But either way, science is an art as well.
Correct. And with that, there's lots of people who use those images. So thank you for your attention.
Are there any questions? Finish off.
Yes.
You said you don't use JPEG, so I'm guessing you don't use bitmaps either. What sort of file formats are these images stored in?
They're either proprietary format that comes from the vendor, but the universal format that we all use is TIFF. Yep.
I understand that you use a lot of confocal microscopy for a lot of your qualitative information. But would you use like flow cytometry for a lot more like on a larger scale for your quantitative stuff?
Look, you've raised a really good point. Okay, microscopy is only one tool in a researcher's toolbox. Okay, and you have to always gain perspective that if you're only looking at one cell in a dish of cells, that you've got to be very careful about generalised readings that you're going to make about it. But note that with flow cytometry, you're back into where I call chemistry land in many ways, because you can't see what's going on. Can you get bulk information through flow cytometry that gives you a holistic idea? Of course you can. But do you understand the nuances of the variability? Not in the same way. Sort of. So but no, flow cytometry is just as an important tool as microscopy. Well, I might be biased in there. I might be biased if I was to answer that one. Yep.
What do you see as the next frontiers in microscopy? Next 100 years?
I think most of it now comes down to two things. The first one is education. Okay? That there are lots of people who think that when you look down a microscope, that it's like a camera, you take a picture and that's it, done and dusted. And I think that there's lots of people who don't get that right. And I think that needs to go through a lot of change. The second thing that I would say is some of these techniques that are around optical sectioning, like light sheet and lattice light sheet, which is allowing you to do things, imaging faster and at higher resolution and pushing it all the time. There are new microscope techniques made every couple of months right now. It's quite remarkable. But signal to noise in the end is what's going to get everything. Okay? The dyes and the specimen preparation is what we'll see all about. So that is your question.
So
Yes.
in your facility, have there been any researchers who try to co-register the images of things, for example, the cancer cell or the ex vivo sample, onto the in vivo bioluminescence fluorescence
Very much so.
imaging data? And how do they do that co-registration?
Look, the closest that they're going to get in that space would be something like they would take an animal and they would do PET or CT and they would be imaging the tumour, for example. Then they would cull the animal and then they would take that out and then they would take that further to the next resolution. Some of the new microscopes that are around, hopefully we'll have ones soon, we've got grants in about it now, is that you can actually take a whole rodent, okay, it's frozen, we use them a lot for these sort of purposes, and essentially it's sliced. And it's sliced in very thin pieces that you can then go and take and do super resolution. So in other words, you can get something that's this big, a whole big picture of it with microscopy type resolution, which is really quite scary. You think 9 terabytes is a problem, this one's going to be just as bad. So in that case, you would take whole animal micro CT data and then you would be able to use this. Does that make sense?
Yes. So what kind of imaging informatics platform would be best to support that kind of integration?
I'm not sure.
Because, 90 terabytes here and then 90 terabytes there from the
Oh, you're asking how do you set up and how do you deal with it?
Yeah.
Oh, that's a whole other talk. I can't get back the last 12 months and
Because I think
spending
the
all that time
future
with
is all
IT.
about that development in that area too, isn't it?
I agree that big data and microscopy is the leading way, and that's when I go overseas. That's what I talk about, and we Harvard and Max Planck and all of us all get together about how we do it. Have we found a solution? We've got a temporary solution that will grow out to 8 petabytes, but will it be enough?
At the other end perspective when it comes to big data, what's the biggest number? at the moment?
Look, in reality, I haven't even seen someone do a 90 terabyte data set, and that's simply because even if they tried to, it wouldn't save time on the station to do that. And it's essentially impossible to move, right? So universities and all around the world need to upgrade all of their buildings, all of their data stores, all of that sort of stuff. For us, 6 terabytes is a common afternoon.
So just to tie in with the previous speaker, where JPEG, where they're not trying to do pixel by pixel, but in this imaging world, it appears to be pixel by
It is
pixel,
pixel by
and
pixel.
there is no mathematical formula to try to reduce.
No, that is not exclusively true. There is compression software that is starting to come available that can take something that's like 6 terabytes and make it 1 terabyte. Okay. What we're testing now and what people are working on around the world is making sure that they don't change those numbers, because in the end, this is for quantification. It's for us to find out what percentage of my drug ended up in the nucleus.
The thing about that as well, though, is that even if you compress it, it doesn't really help you visualize it, because it's got to be uncompressed to actually see it. So all it would ever do is help you storage-wise.
Yes, but it helps you, the researcher, to transmit that data, to analyze it remotely rather than being physically stuck at the facility for, months on end without daylight.
In the solution that we've created, essentially people will take their data, they set it up on the microscope, they let it run, it does it automatically, and they come back 4 hours, 12 hours later, and essentially it will go off-site to a new super server which we've created, and people can log in virtually from anywhere on campus to the analysis stations. They don't ever have to move the data. That's the number one problem. People have to stop moving data around like they used to, because it doesn't exist in this land, not yet. Yes, Pam?
What image analysis software do you recommend for big data?
That's a really good question. Mike, would you like to answer this question? I think we have mixed reviews about it. Right now, I think proprietary software has some limitations, and that's because the way that they thread the processes, some of the conversions are single-threaded, so the sort of compute you need for that is different from the sort of compute that you need to make the actual compute go faster when you're trying to do segmentation of them together. So I think we're starting to favour more things like the big data viewer and some of these other things. Even bar 3D is much better. I'm not a major fan of Aravis at this point in time because it just takes so long. But it's great segmentation.
Yeah, it depends what you want to do, because a lot of the ones will tailor the pipeline for a very specific thing. So as far as Aravis goes, as far as the 3D reconstruction visualization thing, it probably is the best thing out there.
It's one of the only things that can open them. That's out of it.
Yeah, but it's not that it does anything, extremely clever.
Yeah.
It's like anyone
Or you'll
could.
set up an overnight to convert it into a format that it might not chug on, and then it still chugs on it, and then it eventually opens it, and you're like...
I'm going to give you an analogy, and it became very clear to me recently. In the genomics world, they've been making big data, not quite this big data, but big data for a long period of time. You can have your blood taken, and you can get the gene done, and you can have a screen, and all of the rest of it. Right? Lots of privacy issues, lots of ethical issues about it. But they've been dealing with moving that stuff around for about 8 years now. Okay. Now, the biggest barrier that they faced at that time was not actually building infrastructure around it, though it is quite specialised. What it was about was actually commercial software companies, like, for example, Aravis, charging $35,000 per licence, right? Which does not necessarily do a good job, and they would not release the code, because as soon as you release the code, we can manipulate and go and do it for free, right? Researchers are all cheapskates. If we can do it for free, we will. And so once they changed that, and essentially the community all ganged up on all of the illuminated companies and all of these things, eventually they released the code, and that's when things got easier.
But a lot of them as well, like their code isn't actually anything unique. The thing that makes it a pain is that they insist on a proprietary file format that they don't release.
Yeah.
So although they'll do one thing well, once you convert it into that file format and you want to do the next step on it, you can't.
That was an interesting I saw a talk from an astronomer a year ago, and he said, you biologists are nuts, you've got to go to a single file format. And that's something they've done.
Which is why we like the idea of big data viewers. They use HDF5, and there's quite a lot of programs that use that. And it's
most of what we're now working on is creating stuff to write to HDF5, because then everything will be there.
So I think what we're going to need is a martial arts Dropbox.
Very much so.
Thank you very much.